A'udhu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. In today's lecture, we will talk about quantum dots. Quantum dots, especially semiconductor quantum dots. And this title has been taken from the course outline of nanophysics and technology, having the course code of PHY445. Basically, in this lecture, we will discuss the synthesis, fabrication and properties and application of quantum dots. First, we need to know what is quantum dot. So this is very important to us. Semiconductor nanoparticle that exhibit quantum confinement, and its size is typically less than 10 nanometer in diameter. So that are actually quantum dots. In very simple word, we can say that a semiconductor nanocrystals are quantum dot, its property are easily tunable by changing the size and composition of the nanocrystals. So nanoparticle are actually microscopic particle of an inorganic material, maybe CDSE, or organic material, just like a polymer material, and with a diameter less than 100 nanometer. More generally, a particle with diameter less than 1000 nanometer. This is a very general explanation of it. So what are the important properties of quantum dot which make it different from the other materials, and what are the the special properties that are present in quantum dot, and that is interesting to us. The first thing is that it has very high quantum yield, often 20 times brighter than the normal organic phosphors, and it's narrower and more symmetric emission spectra. The spectra which is emitted from quantum dot is more symmetric, and it is 100 to 1000 times more stable to photo bleaching, and it has very high resistance to photo and chemical degradation. We can have a wide range of frequency and wavelength, and in the case of wavelength, the range is wide, and it starts from 400 till 4000 nanometer. So here we can see the peaks and the colors of the quantum dot coming from the quantum dot. Here, when we are decreasing the particle size, we can get different colors. So it's very interesting for us when we reduce the particle size, the color of that quantum dot interestingly change. So what is the phenomena responsible for the light absorption or emission? The first thing we need to know, and we have understood from the very basic modern physics, that is the excitation and de-excitation of electron in a metal. If we consider an isolated atom in a semiconductor, an isolated atom, but in case of bulk crystals, if we consider the semiconductor material, the solid material, so there are bands instead of isolated energy levels, discrete energy levels. So these bands, electron can move in between these bands. There are valence band and conduction band, and upon irradiation of light, radiation of light of suitable frequency, the electron is emitted from the valence. Electron is migrated from valence band toward leaving a hole behind at valence band, and the electron is migrated towards the conduction band. So we have electron hole pair generation process, in which electron hole pairs are generated by the absorption of photon, whose energy is equal to the band gap energy of that particular semiconductors. So this is the simple process. The equation is that photons falls on a semiconductor. So what happens as a result of this photon absorption? An electron present in the conduction band is created, and a hole present in the valence band is created. So this is called as electron hole pair generation. So the electron cannot remain in conduction band for longer time. So it will come back to carry on the de-excitation process. This is actually called as the recombination of electron hole pair, and the recombination results the creation of a photon, and the energy of that photon should be equal to the difference of that energy. So difference of the energy gap, the band gap. So here we can see when an excited electron come back from valence band toward from conduction band toward the valence band, So a photon having energy is equal to h now is emitted, and this could be represented by the equation that electron hole pair recombination lead to the creation of photon. Keep in mind the photon energy should be equal to the difference of the band gap energy of that particular semiconductor. In some cases we have dissipative recombination as well, that in which the energy, but that is within the energy levels, or within the band, or maybe within the conduction band, or within the valence band. I mean, the holes can create the, or maybe some of the states that are created due to the dopant or impurity in the band structures. So that dissipative recombination, I means the energy in that case is converted into heat without creating any light photon. So this is the simple case of electron hole pair recombination, where we have both radiative and non-radiative recombination creating to the photon. And so how we can describe this emission of photon, absorption of photon, emission of photon, and the relationship between the band gap and the particle size? So this could be explained with the help of effective mass model that has been developed in 1985 by Lewis Bros. So it relates the band gap to the particle size of a spherical quantum dot. So this equation is a bit complicated, but anyhow, for general information we have included this equation for the understanding that how the particle size relates or corresponds to the band gap of a semiconductor material. So the average particle size in suspension can be obtained from the absorption onset using the effective mass model, where the band gap that is actually mentioned in electron volt can be approximated by this value. Here the different notation represent different values, just like we have the band gap energy, particle size, mass of effective mass of electron and holes, and even free electron mass, some constant just like a Planck constant, and the charge on electron is also a constant quantity, and relative permittivity, and at the end we have permittivity of free space. So we have different terms in this equation. If you look back toward this equation, we have several terms in this equation, so we need to describe each of the term in the equation in detail. The second term is actually defined is actually the right hand side is the consistent with the particle in a box, that is a quantum confinement models. So it is a quantum localization energy of effective mass ME, and it describes the high electron confinement due to small particle size. It affect the it alter and change the effective mass of electron compared to a bulk material. So it is like a particle that has been closed in a box. We have example from the quantum mechanics where we have studied different phenomena. In some cases we discuss particle in a box, or maybe is a quantum well. It was called as a quantum well. And in some cases we have potential barrier. I mean, so an electron was coming whose energy was less than the energy of the barrier, so that there was some particular tunneling effect or the thing like that. In some cases the particle was confined in a particular well, so I mean the particle energy was less than the energy of that particular well, so that was called as a particle in a well. So in this case is also this second term describe that particular confinement model. So we have this equation that has been 3D box, and its energy is equal to n square h cut square pi divided by 2 m l square, that is equal to further 10h square h cut square divided by 8 m l square. So it's further defined as this equation, and that actually describes the confinement of that particle in a box. It means that particles will be related to that particular energy levels. So the third term in that equation describes the Coulomb attraction between the electron and holes that lower the energy. So it means actually electron and holes are connected with each other with Coulomb attraction, and that account for the interaction of a positive hole, that is actually Me and a negative electron, that is Me negative. So it's actually electron hole is actually the missing electron, so how they interact with each other, and that could be described by the third term in that particular equation. So the electrostatic force is actually calculated by Coulomb law, and here the numerical form of the Coulomb law is present in front of us. F is equal to Q 1 q2 divided by 4 pi epsilon naught r square. Here q1 q2 are the charges on the two charge object. We have a first q1, that is the electron, and the second q2 is actually the hole. So we can calculate the force or the work, the force on that. So the decrease in energy and bringing a positive charge to distance r from a negative charge is given by this equation, where del is equal to integral E square divided by 4 pi epsilon naught r square dr, and this can be further modified into this form. So this is actually this third term in that equation that describes the Coulomb interaction between the two created charges, electrons and holes. So how we can these terms influence the final outcome of these systems? How we can mathematically predict the property of the system? The last term in that is actually negligibly small, and that term one is expressed, it dominates as the radius decreases. So these are actually the ratio or maybe the comparison between different terms, that how it play roles in the modulus. So it means how it can control of the particle fluorescence is possible by adjusting the radius. Here in this corner we can see color, different colors, and behind the color there is also the particle size is also mentioned. Here we can see when we are coming towards the lower particle size, when we decrease the particle size from 7.3 to 4.1 nanometer, the color changes. The wavelength changes that lead to the change in the color. Further decrease in from 4.1 to 2.9 nanometer, the color further changes, and at the end at 2.2 nanometer of the same particle, the same nature of material, we can get very different color. So this is really interesting for us, that by changing the particle size we can get different colors, and that has very interesting application in nanoelectronics. So we can consider some of the quantum confinement in case of some semiconductor material, just like zinc oxide and titanium dioxide. So ZNO has small effective mass, and the quantum effect can be observed for relatively large particle size, and this confinement effect are observed for particle size around or less than 8 nanometer. In this case TiO2 has large effective masses, and in that quantum effect are nearly unobservable. So here we can see the quantum effect and the quantum confinement of the in the case of TiO2 and ZNO. Here in the case of ZNO we can see how the particle size confine the particles in a particular wavelength region. In the case of TiO2 we can also see in this figure that the band gap and the wavelength in nanometer is mentioned. So how it can relate the two with each other with the particle size of that particular materials. So the synthesis or the formation of nanoparticle is very interesting, because we can get very interesting morphologies from some of the semiconductor material, and that interesting morphology can give us very interesting properties. So here in this case we can we have different set of methods for the synthesis of nanoparticles. The synthesis technique is a function of the material and desired size and quantity and quality of dispersion. So some of the synthesis technique are just like vapor phase deposition, in which we have further different categories, just like molecular beam and flame synthesis, etc. Maybe in some solution phase synthesis we have aqueous solution and non-aqueous solution synthesis form. When we create the semiconductor nanoparticle, then we can use that particular method for that, especially from group 1 to group 6 and group 3 to group 5. That is the combination of that particular semiconductor. In some cells, semiconductor nanoparticle could be synthesized with the rapid reduction of organometallic precursor in hot organic with surfactants. So which means is the synthesis of nanoparticles vary from where depends on the nature of that particular nanoparticle what we are dealing with. So it means depends upon the nature of that material, but anyhow some general technique are mentioned here which create or which synthesize or which fabricate some interesting nanoparticle quantum dots. So we have the how the crystallite size increases or decreases. So there are two parallel processes for the explanation of decrease and increase in the particle size. So this is actually the nucleation and growth of the particle size. So we have this actually this is the curve which is showing the nucleation and growth of the particle size. And so this slide actually show how the particle size we can reduce and increase the particle size with the help of nucleation and growth process. So there are different processes responsible for that, and here in the vertical size we can see the increase in the particle size, and downward it can show the decrease in particle size. So the horizontal dashed lines represent the critical concentration for nucleation and saturation of that particle size. How we can keep the quantum dots? Keeping the quantum dots is really very interesting. Maybe covering with other semiconductor materials. So due to the extremely high surface area of a nanoparticle, there is a high quantity of dangling bonds. So adding a capping agent consisting of a higher band gap energy semiconductor, as well, this is called as a semiconductor mixing as well, or smaller, can eliminate dangling bonds and drastically increase the quantum yield. We have performed it for several semiconductor materials. Just like in this case we have CDSE, on which there is the cover of CDS, and finally at the end we have another covering of ZNS. So we can get very interesting property from this material and increase the quantum yield as well. So here we have a PLP spectra and the quantum yield. So it means that and at the horizontal axis we have the reaction time. So how we can improve the quantum yield between the pure and the semiconductor which is doped or which is covered with another semiconductor material. So it is already visible in the curves. So with the addition of the CDS, ZNS, the quantum yield can be increased from 5% to 55%, and that is really very great increase in the quantum yield. So the synthesis typically consisted of lower concentration of precursor injected at lower temperature and at low speeds. So this is some of the images of the quantum dot prepared for different semiconductor material at different resolution. So we can see easily the quantum dots are really visible at over here. So it has very wide range of application. The quantum dot had very wide range of applications, and that had been used in various fields, including the biological sciences as well. So we have magnetic nanoparticle, that is have size nano size magnetic particle, and it has super paramagnetic behavior. So it is widely studied since 1970, and it can it is used specially for the control of the magnetic field. So here we can see the hysteresis loop for this nanoparticles. So the CO has higher concentration compared to the magnetite and this particular material. So here we can see how this the quantum dot has very interesting hysteresis loop. So other application of quantum dots are very interesting. The first thing is we have quantum dot LEDs, light emitting diode, that are made from quantum dot, and it has very interesting application. And these quantum dots are specially used to produce inexpensive and industrial quality white light that is made from quantum dots. The second efficiency of such materials is that it has improved our traditional LED phosphorus integration by dot ability to absorb and emit at desired wavelength, because its light is very narrow wavelength. This is often like monochromatic lights. So when we desire a particular light, so we can create a nanoparticle or maybe quantum dots having the same wavelength. So this is very interesting for us, and we can only deal with the particle size. Changing the particle size will change the created or the absorption or emission spectrum of that particular quantum dot. So we can produce white light by intermixing red, green, blue and blue emitting dots homogeneously within the phosphors. That is this is difficult to accomplish with the traditional LED phosphor. Actually, the other interesting property of quantum dot LED is that Actually, with normal LEDs phosphor, it was difficult to create the white light, but in this case we can create the white light by intermixing the three different colors that are red, green and blue colors, and we can create the white colors. The other interesting application of quantum dots are the solar cells and photovoltaics. In solar cell we can use the quantum dot, that are the traditional solar cells are made of semiconductor. If we see the traditional solar cell is made of semiconductor and expensive, it is comparatively expensive to produce, and its theoretical upper limit is 33% efficiency for conversion of sunlight to electricity for these cells. But if we can use the quantum dot, it allow realization of third generation solar cell having the efficiency of around 60%. That is almost double of the efficiency of traditional solar cells. In electricity production, while being as a $100 or less per square meter of paneling necessary, so it means comparatively it is cheap and more efficient. So this is really interesting, because in semiconductor technology, in our technology, we are needing such material which has improved properties with less and comparatively inexpensive or cheap. So it is effective quantum dots ability to professionally absorb and emit radiation that results in the optimal generation of electric current and voltage. So it is also used in electronics, and that has very interesting application. So this is actually some of the application of the quantum dot in our daily life. Next lecture, I hope we will move towards the fabrication properties and applications of nanowire. This is something about the quantum dots. Thank you very much.